I can't see any CR. Ondari, Liam, Changa, switch on your mic.
Yes.
How come you're logging from outside the university? You're not in the university? Hello, Ondari.
Hello, I can hear you.
Okay, we'll wait for more students. I'm only seeing 12. And time is going. And we lost the other Monday. Any CR, if you're there, any CR, just switch on your mic. Any CR. Why is everybody logging from outside the university? Okay, we'll give them another 5 minutes for the numbers to increase. Because you're supposed to be about 60, over 60. I think Sifrin is the CR. What is he called? Safin?
Fefin.
Huh?
Fefin.
Sifin, why the students? You're very few today. And everybody is
I'm
logging
not
from
sure.
outside. Huh?
I'm not sure whether
And why is everybody logging from outside the university, including you?
I've used
Even you are logging from outside the university. Hmm?
I've used I think when for students email usually looks like you're outside the organization, then the lecturer's email is also different because I'm using the student's email.
Okay. Okay. So when the numbers reach 20, we start. Though you're supposed to be 60. Yeah, so that we don't lose a lot of time, because today we've got only 1 hour. Okay, I'll just start because we've got a lot of derivations to do. So I'll just start. The other people will meet us as we go along. Sifrin, I think you can read. Can you see the presentation on your screen?
Yes, I can.
The size is okay for your laptops?
Yes, it is.
Okay, we'll continue. So in the last class, we wanted to show that this Gilbert's multiplier cell can multiply. And we said it comprises of two differential amplifiers in parallel forming the output, and another differential amplifier comprising of Q5 and Q6 to vary the transconductance. So we did the analysis. We said let the collector currents of Q1 be called IC1 or just I1. And as I said, I'm using capitals, but actually signals. And likewise, the collector current of Q2, Q3, Q4 will be called I2, I3, I4. Collector current of Q5, Q6 will be called I5, I6. And these are the dynamic currents. These are not the quiescent currents for biasing. These are the signal currents. So we came up with some equation. The collector current of Q1 plus the collector current of Q2 should give us collector current of Q5. Because of the assumption that the emitter current is the same as the collector current, because the gains of the transistors are very high. So this is the equations we did through one time. I1, I2 equals I5, I3, I4, I6. And we consider the current relationship between any general differential amplifier for any simple general differential amplifier. Notice minus GM12, where GM12 is the transconductance of Q1 and Q2 into V1RL and V not for this is just a drop across RL minus a drop across RL on the right, map over equation 5. And when you simplify it, we got that V naught is A2 minus I1 in RL, equation 7, but want to put in the form of I1 to get that we get 8 to, sorry, we equate 8 to 4, which is the general equation. It should be the same. So equation 4, then we get this relationship that gives us the current relations over the alpha between the signals of U1, which is the so GM12 V1 is I1 minus other form of what is in the right hand side we put on the left. So I will say, as I've shown in 11 and 12 over here, that I1 minus I2 is equal to GM12 into V1. So if we apply this general relationship of the simple differential amplifiers to the three differential amplifiers, starting with the top. So the first differential amplifier comprises of Q1 and Q2. The next one comprises of Q3 and Q4. So if we apply 10 to them, we'll get equation 11. We'll get equation 11 and equation 12. Just using equation applying the same to Q3 and Q4. And next, we considered the output voltage of the Gilbert's multiplier cell. So for the Gilbert's multiplier cell, the output voltage can be written as the drop across the resistance to the left. Starting from VCC, we drop across the load resistance on the left, and the current passing through the resistance on the left is actually IC1 plus I3. So the drop across the resistance to the left is RL into IC1 and IC3. And the drop across the resistance to the right is actually RL into IC2 plus IC4. So if you start from VCC, drop across the load resistance to the left minus drop across load resistance to the right, we get V naught. So we can write this equation here, that V naught is VCC minus 1 plus R3 into RL, that's the drop across the resistance to the left, minus drop across resistance to the right, which is I2 plus I4 into RL. So if you simplify 13, it's cancel, and then we remain with the equation 15. RL is common in 14, so we can take it outside. So we want to combine the first two currents together. So instead of writing from 15 over here, minus into brackets I1 plus I3, I'll take this I1, so it will be minus I1, and combine it with this positive I2 over here. So I'll get I2 minus I1 into RL, and then combine I3 and I4. So I4 is positive, and from this first bracket over here, I3 is negative. So you get this other second term over here, I4 minus I3 into RL. I just want to put it one that over here. This is the equation we derived. I1 minus I2 is G1 into V1, I1 and I2 first. So from this sequence, one first, I can get to brackets 1 minus 2. Fourth one, 3, can leave it as it is. I can substitute. I can substitute this I1 minus I2 is here. I1 minus I2 is GM12 into V1. I've written it over here. We derived it earlier on. So this first term over here of 17 can be written as minus GM12 into V1, because I1 minus I2 from here is just GM12 into V1. First term is minus I1 I2, or we substitute. We had also derived it over here. It's here, equation 12 over here. You can see it over here. Equation 12, I4 minus I3, we can write it as GM 34 V1. So if I substitute it, we get equation 18. So I take RL in 18, and V1 common, so I take it outside. So we'll get V1 RL into brackets GM34 minus GM 2. This is a simplified form of 18, but we know that GM34 is nothing but I6 by VT. And GM12 is I5 by VT. So if you substitute these results in 19, instead of writing GM34 and GM12 in 19, I can write it as shown in 22 over here. The V1 RL into brackets, instead of GM34, I can write equation 20 over here. I6 by VT minus GM12, which is I5 by VT. So I can now take VT common in the inside bracket and remove it outside. So I'll get V0 is V1 RL over VT into I6. So this gives us a relationship of how the output voltage varies as a function of V1 and I5 and I6. Now to get how the output voltage varies as a function of V1 and V2, remember I5 and I6 are the collector currents of the bottom transistors. I5 will be the collector current here. I6 is the collector current over here. So this I5 and I6, I5, sorry, Q5 and Q6 form a similar differential amplifier to the basic general differential amplifier, what we're calling the first differential amplifier Q1 and the second differential amplifier Q2. The only difference here is that now we've added some resistance, which is called RE, or emitter degeneration resistance. That's the only difference. So we are going to solve this. So we want a relationship between V2 and I5 and I6. How V2 varies I5 and I6. Now we have got two conditions over here. The first condition is when RE is equal to 0. When RE is equal to 0, then this differential amplifier, which comprises of Q5 and Q6, is identical to the differential amplifier, the general differential amplifier, where Q5 was just our Q1 and Q6 was our Q2. So equation 23 is our general output equation, but we're going to find out how I5 and I6 is affected by V2. So for this, we have two cases. Case 1 is where RE is equal to 0. So when RE is equal to 0, so case 1 is RE is equal to 0, and case 2 is RE is not equal to 0. So we'll start with case 1 where RE is equal to 0. So when RE is equal to 0, then the circuit just becomes this circuit over here, where this is Q5 and this is Q6. The collector current of the first one is I5. The collector current of the second one is I6. And just for reference, on the right-hand side over here, I've drawn the general differential amplifier, where the first transistor on the left was Q1, the second transistor was Q2. And we got the voltage current relationship between the current to the first transistor and the voltage V1 applied to the base. So if you look at these two circuits, they're just identical. We just replace Q1 with Q5 in this circuit, and then we replace Q2 with Q6 in this circuit. And the equation will now become, instead of I1, we'll just write I5 minus I6 is GM 5/6 into V2. So that's all we write. So getting the relationship between I5, I6, and V2, we use our general differential amplifier, and these two circuits are identical. It's the namings which is different. So I've said that the current relationship, the current relation, I should put here, is same as that of the general differential amplifier. And then I can say to apply. So applying it to Q5 and Q6. So I'm just applying this equation over here. So instead of I1, I put I6, shown over here. Instead of I2, I put, so instead of I1, I put I5, sorry. Instead of I2, I put I6. And the GMs, now I'll call it GM of transistor 5, transistor 6 is equal to V2. Instead of V1, it is V2. So I've gotten an equation here of how current I5 and I6 varies as a function of V2. Now, in our relationship, let's see, our equation, we want I6 first over here in 23 minus I5. So in this first equation over here, it was I5 minus I6 is equal to GM56 into V2. But if I want to put in the form of I6 first, then I've got to multiply by -1 outside the brackets. Then I'll get I6 minus I5 is GM56 into V2. So in this equation 23 over here, in equation 23, I've gotten I6 minus I5. So all I have to do is to substitute I6 minus I5 to be equal to multiply this equation negative on the left-hand side, on the right-hand side, I get equation 24. So I6 minus I5 minus GM56 into V2, and now I substitute it in this equation 23 over here. So instead of I6 minus I5, I'll write minus GM56 into V2 in 23 here. So that is what I've gotten here, equation 25. Now I have to find out what is GM56. GM56 is, in general, IEE divided by VT. Means the cause, this current over here, this current over here, we normally call it IEE. But its value is actually equal to IT in this diagram. So I'll just put it as IT divided by VT. Okay, so I've taken a shortcut over here, but I've mentioned it over here. So on the right hand side, that would be equation 26. GM56 is IT by VT. So if I substitute this GM56 in this equation 25, 25 looks very far away. deleting even the V2. Okay, let me leave it there. Okay, so if I just substitute for GM56 as IT by VT, then I'll get this equation 26 over here. So in the denominator, I'll get VT squared. And in the numerator, I'll get an IT and V2. So the overall result will be V0 is minus V1 RL IT V2 over VT squared. And we can put in the standard form of the multiplier, where we said the standard form of multiplier is V0 is some scalar into maybe Vx into Vy, where in our case here Vx and Vy are V1 and V2. So we can write this equation 26 as equal to some scalar equal to V1, V2, where the scalar will be RL IT all divided by VT squared. So we've shown that that Gilbert multiplier cell multiplies for the case 1, where the resistance at the emitter was equal to 0. Now let's consider case 2. So let's consider now case 2, where the emitter resistance is not equal to 0. So this is the circuit we have. Well, I know it looks a bit messy. Okay, let me just try and clean it up a bit. So this is our transistor Q5. This is our transistor Q6. And the collector currents are I5 and I6. Now you can see the emitter resistances are there. The emitter resistances are not equal to 0. So the emitter resistance is RE. So now we are considering, if you look at the original circuit of a Gilbert multiplier cell, here's the original circuit. So now we are considering RE is present at the emitters of Q5 and Q6. So how will the result change now? So let's go to the case 2, where the emitter resistance is not equal to 0. So I've drawn another circuit over here just to save time in the analysis. So once again, what we want is the relationship between I5 and I6 as a function of V2. So for this, we'll apply. So I've said here, the current relation between I5 and I6 and V2 are obtained by applying a KVL to the loop A, B, C, D, E. So I've just redrawn it over here, so the diagram is not messy. I've drawn another diagram just next to it. So A is the base of the Q5, B is the emitter, then C is this midpoint of the two resistances, D is the end of this resistance, RE, this is the resistance RE, and E is the base of Q6. So if I start at the base of Q5, the potential is V2. I drop VB5. I drop across this first resistance on the left. So the drop will be I5 into RE. Then I gain a potential here, which is RE into I6. Then again another potential over here, which is VB6, should equal to 0. That is how I get equation 29. So now we just have to simplify equation 29 over here. So I'll make V2 the subject. So the things that are negative on the left-hand side become positive on the right-hand side when placed to the right-hand side. So VB5 will be positive, VB6 will be minus, 5 will be positive, 6RE will be negative. So that's how I get equation 30. Now, to simplify VB5 minus VB6, I'll just put this note over here. We've done it a lot of times that from Ebermold's current relationship, IC is I naught e to the VB by neta. If you rearrange this equation over here, IC divided by I naught is e to the VB, e to the VB divided by neta, then take natural logs of left-hand side, right-hand side. So you get natural log. I thought I'd done it somewhere. I think I'll put the results over here. So this equation over here, if you take natural log of left-hand side, right-hand side, you'll get, let me just do it. This is me talking. So if you take natural logs of this, you'll get natural log of any current IC over I naught is equal to VBE over neta VT. And therefore, we can write that in general VBE is equal to neta VT natural log IC divided by I naught in general. So if it's VB5, then VB5 will be equal to neta VT natural log I5 over I naught 5. If it's VB6, then VB6 will be equal to neta VT natural log I6 over I naught 6. So in equation 31, I'll just simplify the steps over here. So the first term over here in equation 30 is V2 is equal to VB5. But what is VB5? VB5 is neta VT natural log I5 over I naught. So minus VB6, what's VB6? Is neta VT natural log I6 divided by I naught. And if you simplify it, you get this first term over here of equation 31, that V2 is neta VT natural log I5 divided by I6 plus, combine these two terms over here. We got RE common. So you can write this term over here as RE outside the bracket, I5 minus I6. So just to save me typing, I took some shortcuts over there, but it's because those results, we've derived them earlier on. Now, equation 31 can be simplified because remember these currents I5 and I6 are the currents that are passing through the differential amplifier. And I told you that the difference between the two currents of your differential amplifier from your third year electronics is very little. From your study of differential amplifiers, This is your VD, your differential voltage, and this is maybe IEE, the total current, which in our case now is IT. You find that for the first transistor, the current will fall like this, the second transistor. So this could be maybe your I5, and this could be your I6. And if R is equal to 0, this is about 4 VT, which is approximately, VT is 26 millivolts. It's approximately 100 millivolts. When one current shifts from one transistor to the other transistor. Now for small changes in the, or for small differences in current between the two, in equation 31, the natural log, if I5 and I6 are not very different from one another, the natural log of this term over here is natural log of approximately 1, and therefore this first term becomes 0, and therefore V2 is I5 minus I6 only. Now, what I've drawn over here in this graph over here is when VT, sorry, is when RE is equal to 0. So this graph over here is for RE is equal to 0. If RE is present, we shall show this later, is the difference voltage, then you'll find that I6 will be something like that. It won't be a straight, it's almost just a straight line. We shall prove it. Well, this now will be your I5, and this is your I6. And then this voltage will be much, much larger. We shall show it. We shall derive it later on. So let's take it that I5 divided by I6 is approximately equal to 1, and natural log of 1 is 0. So we can approximate that V2 will be approximately equal to I5 minus I6 into RE. So this equation 32 gives us the relationship of how I5 and I6 change as a result of V2. And that is what we wanted. So now we're going to substitute this result in equation 23. And I think I brought, because 23 is where we have passed it a long time, so I've just retyped it over here. Equation 23 was that V naught equals V1 RL over VT I6 minus I5. Okay, maybe some of you are not convinced, so let's just go back to our notes. Here's equation 23. V naught is equal to V1 RL over VT into I6 minus I5. But equation 32, we've got it in terms of I5 minus I6 RL. V2 is equal to I5 minus I6 into RL. So there's supposed to be a minus sign. So if I put I6 first, so here is supposed to be a minus sign, because equation 32 is V2 is equal to I5 minus I6 into RL, but I want it in terms of, in equation 23, in terms of I6 minus I5. So from equation 32, we can write that from 32, we can just write that V2 divided by RE is I5 minus I6. Then the next step, what you want is I6 minus I5. So we can write that minus V2 over RE is I6 minus I5. So that is what I've substituted in 23 over here to get V naught in terms of this. So I've substituted that result in 23. I6 minus I5 is minus V2 over RE, then I get 23. So that the overall result now is V naught is minus V1 RL V2 over V2 over RE. Or if you rearrange it better, V naught is V1 V2 minus just means that the output voltage is inverted. You can convert it back by using another inverter or an amplifier which does not invert. Sorry, an amplifier that inverts. So we get V naught 34. We get V naught is minus V1 V2 RL over VT RE, which can now be put in the standard form that V naught is some scalar into V1 V2. Of course, where the scalar is RL over VT into RE. So the scalar K is just RL over VT into RE. So we've shown both case 1 and case 2 multiply. The only difference now is in the gain. In equation 34, the gain is decreased by a factor due to RE, the emitter degeneration resistance. So the gain will be smaller. When RE is not equal to 0, I think we did it earlier somewhere. When RE is not equal to 0, we got this equation 26 over here, which is V1, V2, RL over VT squared. But now with the emitter resistance, the gain is V1, V2, RL over VT into RE. So actually, as you increase RE, the gain decreases, but the linearity improves. The linearity improves. The input range of the voltage V2 improves. That's why I've drawn this dynamic range over here. We shall see later on. It will be very large. It's a function of RE. Whilst if there's no emitter degeneration resistance, the maximum voltage you can put is about plus minus 100 millivolts over here before the circuit starts to clip. Now let's consider the advantages of this Gilbert multiplier cell. So for the advantages over here, for the Gilbert multiplier cell, the signals V1 and V2 can both take positive and negative values. So the output will be some scalar into plus minus V1 times plus minus V2. And this implies that the output of a Gilbert's multiplier is available in all the 4 quadrants. So the Gilbert's multiplier cell is referred to as a 4-quadrant multiplier. The other advantage of this Gilbert's multiplier cell is that it lends itself to monolithic fabrication. Mono just means single, lithic means rock in Greek. So it's just fabricated in a silicon wafer. We want to put generally in IC form. So there are many companies which manufacture this multiplier chip. As I said, multipliers are very common in communication circuits. Number 3, the bandwidth. Sorry, number 3, large bandwidths are available. These notes of mine, I wrote them some time back, up to 3 gigahertz. Now you could even be reaching 6 to 8 gigahertz now. And is dependent on the current state of the microelectronic technology. And number 5, it gives rise to low-cost IC multipliers due to monolithic fabrication. I don't know how much you did in your fourth year studying logic gates or logic gate-based systems. But you can go to, say, YouTube and go to websites. So go to the sites of companies that fabricate IC chips. They have what are known as fab labs. So people like IBM, people like Intel, ASM of Taiwan. And you can see how they make these chips. Once the first chip is working, then they can actually mass produce them very, very fast. And this gives rise to low-cost production of these IC chips. So that gives us the last point over here. It gives rise to low-cost IC fabrication of monolithic. It gives rise to low-cost IC multipliers due to monolithic fabrication. In a silicon wafer, they can make so many chips out of just a single silicon wafer. If you imagine a processor, say like a Core i5 or Core i7, the size of the die will be very small. It will be less than 1 centimeter by 1 centimeter, but we'll have about over 60 million transistors inside it. So a silicon wafer, which is almost like 10 centimeters by 10 centimeters, we can produce lots of chips on a single silicon wafer. Now, the limitations of this circuit, the Gilbert's multiplier that I've just shown over here, is that number 1 is the range of the signal V1 is less than 4 VT. That's because the top, if you look at the top transistors, look at the top transistors, Q1, Q2, Q3, Q4. These are connected almost in parallel. There's no emitter resistance between Q1 and Q2. There's no emitter resistance between Q3 and Q4. So the maximum signal, differential signal between these 2 points at the input is plus minus 4 VT. Whereas for the second differential amplifier, Q5 and Q6, in case 1, if case 1 the emitter resistance was 0, then the dynamic range of the signal that you can put in V2 will be identical to that of V1. But if you put an RE, then the dynamic range changes. And we shall see that later on. You can make it very large. But the second disadvantage is that if you look at the output is floating. The output does not have a common reference, so it's floating. But this is just the cell in a particular multiplier. We shall see. This output is taken with the reference to the earth, and we know it's easy. Just put a difference amplifier. But we still have a problem is that the reference of the signal V1 and V2 with reference to the ground are different. So we still got a problem to solve. So in conclusion, let's go to a summary over here. So limitation number 2 is that the two signals V1 and V2 do not have a common ground. Number 3, also signal V2 sees an input resistance which is approximately 2 beta Re, while signal V1 sees an input resistance of approximately 2 HIE. So the two sources do not see the same. I should have written here input load resistance. I don't see the input load resistance. So for this circuit with the Re, the input resistance here is much higher than this signal which is applied to these 2 points which go to Q1, Q2, Q3, Q4. So that will have to be sorted out. But at least we've shown that this circuit can multiply, and it's referred to as a 4-quadrant multiplier. Now, let's see. I won't have time now to analyze another circuit, but let's just see a practical Gilbert's multiplier. Let's see a practical Gilbert's multiplier. So this is the circuit of a practical Gilbert's multiplier. Now let's ask questions on this, and very few students get it right. Very few students get it right. So I'll just describe it. I don't have time to do any analysis right now. But if you look at this circuit, this is practical, but it's still not complete. It's just that the page is not enough to contain all the circuitry, and this was drawn by, I had to draw this by using the computer, okay? But in the notes I've sent you, I've sent you some circuits made by companies. So let's look at this circuit over here. If you look here, Q3, Q4, Q5, Q6, this Q9, Q10, this actually forms a Gilbert multiplier cell. This is our multiplier. And they use a slightly different design at the emitter. At the emitter, remember this Q9, Q10 was like our Q5, Q6. But you can see if you follow Q9, the emitter goes through this 25K R1 over here. And the emitter of Q10, which was like a Q6, goes through R1. And then the two are connected through this 36K over here. And then that's when we have a constant current source formed by this transistor over here. It's not very clear even in my drawing. I think this one is Q16. I think Q15. This one should be Q15. And this one Q16. So these are the constant current sources. So the important thing, most companies tend to slightly vary their circuits from the other just to prevent being sued by the other for copyrights. But we'll analyze this circuit and show that also this configuration can be used to multiply. But the Gilbert multiplier cell is formed by Q3, Q4, Q5, Q6. These are our top parallel differential amplifiers. Then Q9, Q10. Now the only difference with the 11 we've shown is that the way the emitter resistance are configured in this case and the way the constant current source are. So we have got two transistors here, this one and this one, forming the current source. Now at the input over here, at the input, which is gives us our supply Vx, goes to Q7 and Q8. This is a special circuit. This Q7, Q8, Q1, Q2. This circuit over here is called a preconditioning circuit. Sometimes it's referred to as a pre-distortion circuit. Its function is to increase the dynamic range of the signal that goes our old V1 signal. Remember our old V1 signal was here. This was our V1 signal. Okay. So V0, I'll call it V01. Is used, or let me just put it simply this way, that this circuit over here, the circuit that comprises Q7, Q8, Q1, Q2, I said it's called a preconditioning circuit. It makes the signal that goes to V1, which is our normal Gilbert multiplier cell, be such that we can extend the dynamic range of our Gilbert multiplier cell. And it does so by distorting the signal with a tan hyperbolic inverse function, which we shall see later on. Because if I just apply signal to V1, the maximum signal I can put there is plus minus 4VT, which is just plus minus 400. Sorry, plus minus 100 millivolts, 26 times 4 approximately. But by connecting this pre-distortion circuit and applying the signal as shown over there, Vx to the base of Q7 and 8, I can get a dynamic range. I can apply signal at the input here. I think this is Vz, and this one is Vy. My eyes are not very good. Okay, I think the signal is Vz. And the other signal here is Vy. So by applying a signal at Vz, I can increase the dynamic range of that signal to be approximately plus minus 10 volts. And then the signal Vy will also be plus minus 10 volts. And then now the beauty of this circuit is that both the signals Vz and Vy are now with reference to the ground. So the only remaining problem is to make the output to be with the reference to the ground, because we want a multiplier, which I said the output V0 is with reference to the ground, and the signal Vx, or in our case over here, Vz, is reference to Y. Let me just put Vx and Vy, general. So that is what we want. So in the next class, we shall analyze the Gilbert multiplier cell and show that with this configuration also, we are able to multiply. So I'll deal with the Gilbert multiplier cell with this with the emitter resistance at Q9 and Q10, having some value R1 in the 35K, and then case 2, I'll consider when R1 is 0. In fact, I'll start with the R1 is equal to 0. Then case 2, R1 is equal to 25K. Then show that the cell itself can multiply. Then later on in another analysis, we shall show the function. We'll analyze this circuit, which comprises of Q7, Q8, which is referred to as the predistortion circuit or preconditioning circuit, and see how it extends the dynamic range of the signal V1, which was input to the basic Gilbert multiplier cell, said that it's approximately equal to plus minus 10 volts. So it's approximately equal to the dynamic range of the signal Vy in this circuit. So I'll stop over there. CR, maybe you can tell me, I'm only seeing 39 of you. What the rest of you?
I'm not sure.
Hmm?
I think we dropped off in the middle of the class, maybe network issues.
Okay, so I'll stop over there unless there's any questions. I'd asked you in the last class to bring the circuit that you're doing in the lab, but you guys don't come to class in time, so I lose 10 minutes, and then I got to cover what I'm supposed to teach. Because if people are complaining the circuit you're doing in the lab is not working, so I wanted to see this circuit. Are you told to design your own multiplier circuit, or all of you are using a standard circuit, CR?
Right, you design your own.
Okay. Okay, then we'll stop over there for today.